So welcome to the third lecture on quantum field theory. So in today's lecture, we are going to discuss some of the motivation for why we need quantum field theory. So historically, quantum field theory arose in an attempt to unify quantum mechanics with special relativity. This led to the discovery of quantum field theory. So we will discuss some of the motivation or some of the difficulties and challenges that physicists faced in trying to make this unification work. So let's start with the abstract form of Schrodinger's equation. So Schrodinger's equation tells us that the time derivative of the wave function is proportional to the Hamiltonian operator acting on the wave function. So in non-relativistic quantum mechanics, we know that for a free particle, for example, if I take a free particle, then the Hamiltonian is given by the kinetic energy, p squared by 2m, which if you write it in terms of the operators in the position representation, it's given by h bar squared by 2m delta squared. So Schrodinger equation in non-relativistic quantum mechanics has this form. And this is a wave equation, but this is not a relativistic wave equation. And that fact should be obvious from the fact that this is first order in time. This is first order, whereas this is second order in space. Special relativity treats time and space on an equal footing. And therefore, if you expect a wave equation that is compatible with special relativity to have the same order both in space derivative and time derivative. Before we move on and propose some equation where quantum mechanics and special relativity may be unified, let us take an aside and discuss a relativistic form of a wave equation. Let us just discuss what a relativistic wave equation might look like. So this is an aside, and the aside is about the example of a Lorentz-Invariant wave equation. As you know, Lorentz transformations are the transformations of special relativity, and therefore, when we say Lorentz invariant, we mean relativistic. Okay, let's define an operator denoted by box, and it's given by 1 by c squared, where c is the speed of light, partial derivative squared with respect to time minus the Laplacian operator. So this operator, box, is called D'Alembert or the D'Alembert operator. And the D'Alembert operator is the four-dimensional analog of the Laplacian operator, which is this thing. Now, the D'Alembert operator is an useful operator or an useful gadget when we are trying to formulate a relativistic wave equation. So to see that it's relativistically invariant, let us introduce this derivative operator, del mu, and del mu is given by d by d x mu. And the different components of this is given by the spatial component is del by del t times 1 by c So that's the time component, and the spatial components are given by the spatial derivative operator or the gradient operator. So then the D'Alembert operator is then defined to be eta mu nu. Remember, eta mu nu is the inverse metric of Minkowski space del mu del nu. And we can always use eta to raise and lower indices. So we can use this to write the first derivative as del upstairs mu, and the second one is then del mu. So this is another form of the D'Alembert operator. Now, recall that from your course in, say, tensor analysis, that what the definition of a covariant vector is. So suppose that we make a transformation, a coordinate transformation where x mu goes to x prime of mu equal to delta lambda mu nu x of nu. So for us in special relativity, these lambda matrices are going to be the Lorentz transformation matrices. But in the language of tensor analysis, this could be any arbitrary transformation. This doesn't have to be necessarily a Lorentz transformation. It could be some other type of transformation. So under such a transformation, the definition of a covariant vector is a vector which has an upstairs index, which under, say, the above transformation, transforms in this way. So you might say, why aren't we calling x mu a covariant vector? Well, that's because x mu is actually a coordinate. Technically, it is not a vector, and you can show that the object that is a contravariant vector, is delta of x mu. So anyway, this is something beyond this course, so I'm not going to go into that. So this is the definition of a contravariant vector. So similarly, a covariant vector is something which has a downstairs index, and under this transformation, it transforms as W mu downstairs goes to, you have the inverse matrix lambda, and here you have nu mu W nu downstairs. So this is the definition of a covariant vector. So as I said before, in special relativity, these matrices, lambda mu nu, these are the Lorentz transformations or transformation matrices. And they have a special property, and the property is that when you contract the two Lorentz transformation matrices with the metric tensor, then you get the metric tensor back. So such, as a result of this, so the metric tensor, recall, in our convention, the only non-zero components are the diagonal bits. So therefore, you can show very easily that if I contract the metric tensor with its inverse, by the way, the inverse of the metric tensor in this case is the same as the metric tensor. But if you contract the metric tensor with its inverse, you get the Kronecker delta function, which is just the identity matrix. Now, another fact is that the metric tensor can be used to raise and lower indices, and we can use that in this equation. And we write this equation in the following form. We can lower one of the indices from the first matrix, and that becomes nu alpha, and then I've got nu lambda nu beta, and that's equal to eta alpha beta. Now what we can do is that we can use this identity to contract a factor of eta with this equation and raise one of the indices. Say we can raise say the alpha index. So if I do this, then you can show very easily that this thing is then delta alpha beta. So this shows that this matrix is nothing but the inverse matrix of this matrix, and therefore its index structure should be the same as this matrix, and therefore it should have this should be alpha and this should be nu, and then we should have lambda nu beta equal to delta alpha beta. So now if I go back to my transformation of the covariant vector, which was, W prime was given by lambda inverse, and then we had mu here and nu here, and W nu here. Then using this, what we can do is we can see that this thing is equal to this thing, and therefore we can write this as lambda mu nu W nu. So in other words, this is how covariant vectors transform. So another thing I want you to notice is that eta, say upstairs, and this also holds for downstairs, what I'm going to show you. This transforms as eta prime mu nu is equal to lambda mu upstairs, alpha downstairs, lambda nu upstairs, beta downstairs, eta upstairs, alpha beta. Now, because it's a Lorentz transformation, we know that this must be equal to eta mu nu. And therefore, we see that under a Lorentz transformation, the eta tensor does not change. So eta mu nu upstairs and eta mu nu downstairs are special kind of tensors, and they're called invariant tensors. A general tensor will satisfy this, but it will not satisfy this. So invariant tensors are a very special kind of tensors. Now, let us go back to our original Lorentz transformation, which was x prime of mu is given by lambda mu sigma x sigma. And then what we've done is that we've figured out what the inverse transformation is, and we apply the inverse transformation. Then what do we get? Well, we multiply both sides by lambda mu alpha. We contract the mu index, and then we have lambda mu alpha, lambda mu sigma x sigma, and then on the right hand side from this thing we get delta alpha sigma x of sigma, and therefore this is going to be x of alpha. And therefore we get that x of alpha is equal to delta mu alpha, lambda mu alpha x prime of mu. So what we've done is that we have inverted this relationship. And when we've done this, what we can do is that we can then figure out what del prime of mu is. Well, del prime of mu is del by del x prime of mu. But this is nothing but del of x alpha by del x prime of mu times del by del x alpha. But this we can evaluate using this equation. If we take the derivative of that equation, what do we get? We get a delta here, and then we get mu here, and we get alpha here. And this thing we can write as del by del alpha downstairs. And therefore we see that del mu downstairs transforms as del prime of mu is equal to lambda, say mu alpha delta alpha. Now one has to be a little bit careful about transforming derivatives. This is something that doesn't make sense in curved space-time and also in coordinate system, which is not the Cartesian coordinate. But since we are in flat space-time and we're using Cartesian coordinates here, we don't have to worry about that. So having seen how del downstairs mu transforms, it's now easy to kind of show that, this thing, which is the transformed D'Alembert operator, is nothing but two factors of the Lorentz transformation matrices, each of which are inverses of each other. This should be beta. And because these are inverses of each other, we get a delta, and therefore we get del mu, which is just delta. And so if psi is a scalar, is a Lorentz scalar, which means that under Lorentz transformation, psi goes to psi prime, but it doesn't have any factor of Lorentz transformation matrix. This is the definition of a scalar. Then if psi is a solution of this wave equation, then it is also a solution of, then this is equal to this. And therefore, they're the same wave equation. In other words, this equation is a Lorentz-invariant wave equation. Now, what if instead of psi, we had the wave operator, the D'Alembert wave operator, acting on, say, a contravariant vector, and it gave me some other contravariant vector. So this could be, say, in electrodynamics, this could be the 4-vector potential, and this could be a source where J mu could be the 0th component is some charge density, and the 3 components are the current density. So this is an equation you can derive from Maxwell's equation. So if that is the case, then under a Lorentz transformation, V mu, because it's a contravariant vector, will transform as V prime of mu, and that's equal to lambda mu nu V nu, and J mu will transform in the same way, J prime of mu, and then lambda mu nu J nu, and then this equation then becomes delta lambda mu nu V prime of nu, V of nu, and is equal to lambda mu nu J of nu. But of course, these are invertible matrices, so if you multiply it by its inverse, we get delta nu is equal to J nu. So equation which transform under Lorentz transformation in this way, they are called covariant equation. The covariant here has nothing to do with whether this index is covariant or contravariant. Covariant means that something that transforms in a tensorial way. So we see that under Lorentz transformation, this equation transforms in a tensorial way. But of course, you can always apply an inverse matrix and then see that this equation is nothing but our original equation. So covariant equations are also invariant equations.